Over 8.7 million tons of copper scrap are recycled every year. That's enough to build over 1,500 statues of liberty. But how does old wiring, plumbing, and electronics transform into pure, reusable copper? From collection to melting, this is how over 30,000 pounds of copper are recycled each minute in a factory. Copper is everywhere. Inside of your phone, running through the walls of your house, powering your appliances, and even bringing you fresh water. It's one of the most useful metals in the world, and we've been using it for over 11,000 years. Why? Because copper is an incredible conductor of electricity and heat, making it essential for everything from high-tech electronics to simple plumbing pipes. But here's something even more impressive. Copper never wears out. Unlike other materials that degrade over time, copper can be recycled over and over without losing any of its quality. That means the same piece of copper that was used in an ancient tool thousands of years ago could still be in circulation today, now powering a modern city. So, how does this endless recycling process work? Let's take a trip inside the factories that turn piles of old, discarded copper into brand new high-quality metal. Of course, it all starts with collection. But it's not as simple as just gathering old copper and tossing it into a machine. Every day, tons of scrap copper are collected from all kinds of sources: demolished buildings, old vehicles, broken electronics, and outdated plumbing. Copper is found in electric motors, transformers, circuit boards, and even air conditioning units. So when these items reach the end of their life, their valuable copper components are removed and set aside for recycling. This collection isn't random. Electricians, plumbers, and demolition workers all play a part in saving copper from landfills because they know just how valuable it is. And they're right. A single 100-pound bundle of scrap copper can bring in anywhere from $100 to $400 at a recycling yard, depending on how pure it is. This fluctuating price comes from copper's massive demand. It's needed in everything from construction and power grids to electric vehicles and wind turbines. That's why recycling copper isn't just good for the environment, it's a huge global industry that saves billions of dollars every year while keeping the essential metal in circulation. At the scrapyard, the first big step in copper recycling begins: sorting. Copper comes in many different forms, and not all copper is created equal. Electrical wiring, for example, might look the same at first glance, but the amount of pure copper inside varies. Some wires are thick and nearly solid copper, while others are thinly coated with insulation or mixed with aluminum. Meanwhile, solid copper pieces like pipes, old machinery parts, and heat exchangers need to be separated by grade, since even tiny impurities can affect the metal's conductivity and strength. That's a big deal for industries that rely on ultra-pure copper for power lines, computer chips, and high-performance electrical components. To speed up this process, factories use high-tech sorting machines. One of the first steps is magnetic separation, which removes any steel or iron that might be mixed in. Copper itself isn't magnetic, so these metals can be easily pulled out before they reach the next stage. Another method, called eddy current sorting, takes things even further. This system uses powerful magnetic fields that create electric currents in the metal, forcing copper and aluminum to repel away from each other so that they can be sorted automatically. Once everything is properly sorted, it's time for the next step: shredding. This is where copper scrap is broken down into smaller, more manageable pieces. Recycling plants use massive industrial shredders equipped with razor-sharp rotating blades that can cut through wires, pipes, motors, and even entire radiators in just seconds. These machines are so powerful that some can handle over 3,000 kilograms, which is more than 6,600 pounds, of copper per hour. Before the shredded copper moves forward, it often goes through one more refining step: granulation and separation. This is where the copper is broken down even further into tiny granules, making it even easier to melt. But there's still some leftover insulation, plastic coatings, or other materials mixed in, and they need to be removed. That's where dry separation comes in. These high-tech machines use air separators and vibrating tables to sort out anything that isn't pure copper. Air separators work by blowing a strong stream of air through the granules, lifting away any lightweight materials like plastic, while the heavier copper falls through. Vibrating tables, on the other hand, use controlled shaking to separate materials by density, ensuring that only clean, high-purity copper moves forward. By the time the process is done, the copper is free of contaminants and ready for the most intense step yet: melting. They're fed into massive industrial furnaces that reach temperatures over 1000 degrees Celsius, hot enough to turn solid metal into a glowing liquid state. To put that into perspective, that's nearly twice as hot as molten lava. Some of the largest copper recycling furnaces in the world can process hundreds of tons at a time, keeping up with the never-ending demand for copper. But melting isn't just about turning solid metal into liquid, it's also about purification. Even after all the sorting and shredding, tiny bits of insulation, rubber, and other metals may still be mixed in. As the copper melts, these unwanted materials float to the surface, forming a layer of slag. Workers then skim off this waste, leaving behind cleaner copper. Some factories take it a step further by injecting oxygen into the furnace, which burns off remaining impurities and leaves the molten copper nearly pure. At this point, the copper is almost pure, but not quite. That's where electrolysis comes in, a process that takes recycling to the next level, ensuring that the copper meets the highest industry standards for conductivity and strength. This step happens in massive electrolytic tanks, where slabs of impure copper, called blister copper, are submerged in a solution of copper sulfate and sulfuric acid. Alongside them, thin sheets of pure copper foil act as the collection points, or cathodes. Then, when an electric current is passed through the solution, something incredible happens. Copper atoms leave the impure slabs, dissolve into the liquid, and then reattach themselves to the pure copper sheets in perfect uniform layers. This process takes about 1 or 2 weeks, but the result is totally worth it. Each sheet grows into a solid 300-pound slab of 99.9% pure copper. That's the highest level of purity achievable through recycling, making it just as good as freshly mined copper. But the real bonus of electrolysis? It doesn't just recover copper. As the impurities separate, tiny amounts of gold, silver, and nickel sink to the bottom of the tank, forming what's known as anode sludge. This sludge is collected and processed separately to extract these valuable metals, an extra benefit that makes copper recycling even more profitable and sustainable. Once the copper is fully refined, it needs to take on a solid form before it can be reused again. Factories pour the molten metal into molds, shaping it into ingots or billets, large blocks of pure copper that are easy to transport and process. To cool them quickly and maintain their strength, high-pressure water jets blast the metal, solidifying it in seconds. This rapid cooling keeps the copper's structure intact, ensuring it remains strong and durable for its next life cycle. But these solid blocks aren't the final product. They're just the starting point for the next big transformation: extrusion and fabrication. In this stage, copper ingots are reheated and pushed through extrusion dies, stretching them into long, continuous shapes like wires, tubes, and sheets. This is how we get the copper pipes used in plumbing, the wiring that powers homes and electronics, and the thin copper sheets used in renewable energy systems. Copper's incredible flexibility means it can be bent, shaped, and customized into thousands of different forms. Whether it's being used in electrical grids, cars, or high-tech gadgets, recycled copper is just as valuable as newly mined copper. Only it comes with fewer environmental costs. Recycling copper isn't just smart, it's essential. It takes 85% less energy than mining new copper, saving resources while keeping millions of tons in circulation. In fact, 2/3 of all copper ever mined is still being used today, thanks to efficient recycling. Beyond saving money, it cuts pollution in a big way. Every ton of recycled copper prevents 15 metric tons of CO2 emissions, reducing the need for destructive mining. In the US alone, copper recycling eliminates 186 million metric tons of CO2 annually. Globally, 8.7 million tons of copper scrap are recycled each year, keeping valuable materials from going to waste. And the process keeps getting better. Take the super strip machine, which removes plastic insulation from copper wiring without burning it. Older methods wasted 30% of the copper's weight and released toxic fumes. This new tech preserves every bit of copper while keeping the air clean. As recycling plants handle more electronic waste, they're recovering copper from old phones, computers, and even electric vehicle batteries. Advanced shredders and separators extract copper along with gold, silver, tin, and nickel, making sure nothing valuable is lost. But not all copper is pure. Some is mixed with lead, tin, or zinc, which can't be used in high-tech applications. To fix this, factories melt and refine these alloys, turning them into durable materials for pipes, machinery, and even musical instruments. Even heavily contaminated copper gets purified and reused, keeping waste to a minimum. Factories also work to cut emissions and pollution from the recycling process itself. High-tech filtration systems and scrubbers trap harmful fumes, making the process cleaner and safer. And with global demand for copper skyrocketing, recycling is more crucial than ever. By 2030, e-waste alone is expected to hit 74 million metric tons per year. Recovering the copper inside will help industries grow sustainably without draining natural resources. Right now, factories around the world recycle over 30,000 tons of copper every single minute. That's an entire semi-truck's worth of metal processed in just 60 seconds. It's a perfect example of how recycling isn't just about reducing waste, it's about using what we already have in the smartest way possible. And that's how over 30,000 pounds of copper are recycled every minute, giving it endless new uses while saving energy and reducing waste. Which part of this process surprised you the most? Let us know in the comments below.
What if we told you that every glass bottle you toss in the recycling bin can come back as a new bottle in as little as 30 days? Or that recycling glass saves enough energy each year to power entire cities? From the shattered remains of bottles to the glowing furnaces that melt them into a brand new future, this is how 100 million tons of glass are recycled every year in factories across the world.
Glass is an incredible material. It's durable, versatile, and endlessly recyclable. But here's the thing. It doesn't decompose. A single glass bottle can sit in a landfill for up to 1,000,000 years. That's right, 1,000,000 years. Thankfully, we found a way to turn this environmental challenge into an opportunity through the marvels of glass recycling. The journey begins with collection. Around the world, glass is gathered through a variety of systems tailored to local infrastructure and habits. Many cities rely on curbside collection programs, where residents separate their glass waste into specialized bins for easy pickup by waste management trucks. In other areas, centralized drop-off points allow people to bring their glass items to dedicated containers, often sorted by color. Some regions incentivize recycling through deposit refund systems, where returning bottles can earn small cash rewards or grocery discounts. In European countries, this is a routine practice, fostering widespread participation and higher recycling rates. Conversely, in some parts of the world, glass collection is carried out informally, often by marginalized groups who sell the gathered glass to recycling facilities. Once collected, the glass is transported to sorting centers or recycling plants. Trucks filled with glass bottles, jars, and other items deliver their cargo to facilities designed to handle large volumes of material. At the plant, the first step involves unloading the glass into holding containers, where it's prepared for the next stages. The process may seem straightforward, but it's far from simple. Sorting is a crucial step in glass recycling. Glass comes in 3 primary colors: clear, green, and amber, and each has specific uses in manufacturing. Mixing colors can compromise the quality of the final product, so sorting by color is essential. This task is handled by advanced optical sorting machines equipped with lasers and sensors. These machines analyze each piece of glass as it moves along a conveyor belt, identifying its color based on the light it reflects. Once identified, the machine uses air jets or mechanical systems to direct the glass into the appropriate category. These machines operate at remarkable speeds, sorting tens of thousands of glass fragments every minute with incredible accuracy. But sorting by color is only part of the equation. Contaminants like labels, caps, adhesives, and food residues are some of the biggest challenges in glass recycling. Removing them require multiple stages of cleaning. First, magnets extract ferrous metals, such as steel caps, while electromagnetic separators tackle non-ferrous metals, like aluminum. These systems are powerful enough to remove even tiny fragments that might otherwise go unnoticed. Next, pneumatic systems blow away lightweight contaminants, including plastic and paper, using controlled air currents. For glass intended for food or beverage containers, wet cleaning processes ensure thorough removal of stubborn residues. These washing systems use water jets and mechanical scrubbers to eliminate adhesives, dirt, and organic matter, leaving the glass spotless. This meticulous process is essential for maintaining the quality and safety of recycled glass products. Once the glass is clean and sorted, the next step is crushing. The glass is fed into powerful crushing machines, which break it down into small, uniform pieces known as cullet. These machines come in various types: hammer mills, jaw crushers, and gyratory crushers, all designed to reduce the glass to a specific size. For instance, hammer mills pulverize the glass with rotating hammers, while jaw crushers use a stationary plate and a moving one to crush the material. After the initial crushing, the cullet is sifted using vibrating sieves. These machines separate the glass by size, ensuring a consistent particle size for the next stage. Oversized pieces are sent back through the crusher to minimize waste. Uniform cullet is easier to handle and melts at low temperatures, making it an essential part of the recycling process. Also, cullet melts at a lower temperature than raw materials, saving significant energy during the production process. Crushing is not just about reducing the size of the glass, it also makes the material easier to handle and prepares it for melting. Now comes to the melting stage, where the real transformation begins. The cullet is transported to industrial furnaces that operate at temperatures as high as 3,000 degrees Fahrenheit. Inside these furnaces, the cullet liquefies into molten glass, ready to be shaped into new products. One of the most significant benefits of recycling glass is its energy efficiency. Because cullet melts at a lower temperature than raw materials, it reduces energy consumption by up to 30%. Every ton of recycled glass saves more than a ton of natural resources, including sand, soda ash, and limestone. Many modern furnaces are powered by renewable energy sources like wind or solar, further minimizing the environmental impact. Massive electrodes inside the furnaces sustain the intense heat, while sophisticated systems regulate the temperature and prevent energy loss. Once liquefied, the molten glass is shaped into new products. The liquid is poured into molds to create items such as bottles, jars, and decorative objects. Factories rely on automated systems to ensure precision in shaping, with molds designed to meet exact specifications. But recycled glass isn't limited to traditional uses. In the construction industry, for example, it's used as an aggregate in concrete and asphalt, adding durability and aesthetic appeal. It's also transformed into fiberglass insulation, which helps improve energy efficiency in homes and buildings. Beyond that, recycled glass finds its way into art and design projects, becoming countertops, tiles, and decorative elements. After shaping, the glass is slowly cooled in a process called annealing. This step is very important because it prevents cracks and makes the glass strong and durable. Once the glass is cooled, it goes through quality checks. Machines with cameras and sensors inspect each piece for problems like cracks, bubbles, or uneven shapes. Any item that doesn't meet the standards is sent back to the start of the recycling process, making sure nothing is wasted. But the process does face some challenges. Contamination is a big problem, especially when materials like Pyrex, ceramics, or heat-resistant glass mix in. These materials melt differently and can disrupt the recycling process. To solve this, advanced sorting machines, including AI-powered technology, are being used to detect and remove these items more effectively. Transportation is another issue since glass is heavy and costly to move over long distances. Many recycling plants are now focusing on local operations to cut down on these costs and reduce emissions. New technology has been essential in solving challenges in glass recycling. AI and automation have made sorting and processing much more accurate. Some factories now use closed-loop systems, where recycled glass stays on site and is reused without leaving the facility. Lightweight glass designs are also becoming popular because they use less material and are easier to recycle. These innovations are making glass recycling more sustainable and cost-effective. The environmental benefits of recycling glass are huge. Every bottle recycled means less waste in landfills and fewer greenhouse gases released into the air. Unlike many other materials, glass can be recycled endlessly without losing its quality. This makes it one of the most sustainable materials that we have. Recycling also saves natural resources, like sand and limestone, and uses much less energy than making new glass from scratch. Together, these benefits show how important glass recycling is for protecting the planet and fighting environmental problems. The uses for recycled glass go way beyond making new bottles and jars. In construction, crushed glass is used in roads and building foundations because it's strong and eco-friendly. In farming, tiny glass particles are used to improve soil by helping it hold water and stay healthy. Artists and designers also love recycled glass for making countertops, tiles, and other creative pieces. It's a great example of how recycling can lead to innovative and useful ideas. Looking ahead, the future of glass recycling is exciting. Governments and organizations are working on better ways to collect and recycle glass while encouraging more people to participate. Scientists are developing systems where glass can be recycled endlessly without any waste. New technologies, like AI sorting machines and furnaces powered by renewable energy, are making recycling faster and better for the environment. With these improvements, glass recycling is set to become a big part of creating a greener and more sustainable world. And that's how over 100 million tons of glass are recycled every year, from the initial collection to the advanced sorting and melting that turns waste into valuable new products.
What if yesterday's newspaper could be turned into brand new packaging in just a few weeks? Recycling 1 ton of paper saves 17 trees, 30,000 liters of water, and enough energy to power a home for 6 months. And with over 50 million tons of paper recycled every year, this process keeps billions of sheets out of landfills. From collection to pulping to drying, this is how over 50 million tons of paper are recycled each year in factories. It all starts with collection. From homes, schools, offices, and factories, paper waste is gathered on a massive scale. Curbside recycling programs make it easy for households to toss old newspapers, magazines, and cardboard into bins, where they're whisked away for processing. And offices churn out mountains of shredded documents, which are then bundled up and sent directly to recycling centers. Printing companies and paper manufacturers do their part too, making sure defective or excess paper rolls go straight back into production instead of being wasted. Supermarkets and distribution centers, they return stacks of cardboard boxes and packaging materials, keeping the cycle going. Once collected, the real journey begins. Massive trucks packed with mixed paper waste roll up to material recovery facilities, or MRFs, giant sorting centers where discarded paper starts its transformation. But before a single scrap is processed, there's an important step: weighing in. Each truck is driven onto an enormous industrial scale where the total load is measured. This isn't just for paperwork. It helps track how much material is being processed and keeps the facility running smoothly. Too much paper coming in too fast, the system could clog up. Too little, the plant might not operate at full capacity. After weighing in, the trucks roll onto the unloading zone and tip their cargo onto the intake floor. Within minutes, mountains of used paper rise up. Crumpled newspapers, shredded office documents, flattened cardboard boxes, and glossy magazines, all piled up together in a chaotic mess. Some facilities handle hundreds of tons of material every single day, and without a well-organized system, it would be impossible to process everything efficiently. That's where the heavy machinery comes in. Giant front-end loaders get to work, pushing and spreading the piles into sections, feeding them into the sorting systems like an assembly line. This is where the real transformation begins. Not all paper is created equal, and sorting is crucial to making sure everything ends up where it belongs. Office paper is high quality and can be turned into fresh printing sheets, while thick corrugated cardboard is better suited for new shipping boxes. Glossy magazines and catalogs, coated in shiny finishes, require extra processing to strip away inks and coatings before they can be recycled. Then there are materials that seem like paper, but don't quite make the cut. Thermal paper receipts, wax-coated containers, and laminated sheets contain chemicals that make them unsuitable for recycling. Padded envelopes and food packaging, some have hidden plastic or foil layers that need to be separated before they can move forward. Contamination is the biggest obstacle at this stage. Greasy pizza boxes, paper soaked in food waste, or envelopes still covered in tape can ruin entire batches of recyclable material. Oil interferes with the way paper fibers bond together, and certain coatings prevent proper breakdown. Even tiny things, like staples, plastic windows and envelopes, or glue from sticky notes, need to be removed to keep the process running smoothly. To clean up the mess, recycling facilities rely on both human workers and high-tech machines. Conveyor belts carry the mixed paper through different checkpoints where workers quickly pull out obvious contaminants, plastic bags, food packaging, or anything that doesn't belong. But people can't catch everything, so machines take over next. High-speed sorting systems use spinning discs, air blowers, and infrared scanners to separate paper based on weight, thickness, and material type. Lightweight office paper falls through screens, while heavier cardboard moves to a separate conveyor. Optical sensors analyze each piece, using bursts of air to push non-recyclable materials off the belt. Some facilities even use color sensors to separate white office paper from lower-grade materials, ensuring the cleanest possible batches. Once the human sorters have done their part, it's time for the machines to take over. High-speed optical scanners use infrared light to analyze the composition of each of paper, sorting them with impressive precision. Thick, sturdy materials like corrugated cardboard head down one conveyor, while lighter materials like newspapers and office paper take a different route. Air jets assist in the process, giving lightweight materials a little push to separate them from heavier ones. Some facilities even use color sensors to detect and remove brightly dyed or heavily printed paper, since these can affect the quality of the final product. With the sorting complete, the paper is packed into giant rectangular bales. Each bale is tightly compressed, weighing up to a ton, roughly the size of a compact car. Stacks of these bales fill warehouses, ready to be loaded onto trucks and shipped to paper mills, where the real magic happens. When the bales arrive at the mill, they're not fed into the machines right away. First, they undergo inspection. Contaminants like bits of plastic, stray pieces of metal, or non-recyclable paper have to be removed before processing can continue. Once cleared, the bales are dropped into massive pulping machines like industrial-sized blenders. These pulpers are filled with warm water and special chemicals designed to break down the paper into individual fibers. The spinning blades inside churn everything together, turning old newspapers, office documents, and cardboard boxes into a thick, slushy mix called pulp. The amount of water used in this step is staggering, but modern paper mills have found ways to make the process more sustainable. Many facilities filter and reuse the water multiple times, reducing waste and keeping the system as efficient as possible. But this pulp isn't quite ready to be turned into new paper yet. It's still filled with ink, glue, and tiny plastic bits from labels and coatings. The process begins with mesh screens that work like sieves, allowing fine paper fibers to pass through while trapping larger debris like staples, paper clips, and leftover bits of tape. Next, the pulp moves into high-speed centrifuges. These machines spin the mixture rapidly, separating contaminants based on weight. Heavy particles such as dirt, sand, and tiny metal fragments sink to the bottom, where they're removed. Meanwhile, lighter materials, like glue residues and plastic films, float to the top and are skimmed away. One of the trickiest parts of the entire process is removing ink. If the ink isn't fully extracted, the final paper could come out with some grayish specks or an uneven color, making it look low quality. To tackle this, mills introduce a combination of chemicals and air bubbles into the pulp. The ink particles stick to the bubbles and rise to the surface, forming a foamy layer that's skimmed off and discarded. This method, known as flotation, is incredibly effective at pulling ink away from the fibers. Some mills go even further, using additional washing techniques with water and surfactants to remove stubborn ink particles, ensuring that the pulp is as clean and as pure as possible before moving to the next stage. If the final product needs to be bright white, a little extra whitening magic happens at this stage. Inside of harsh chemicals, modern mills use hydrogen peroxide and oxygen-based solutions to bleach the fibers without breaking them down. But not everything needs to be a crisp, clean white. Newsprint, cardboard, and some packaging materials skip this step entirely, keeping their natural, slightly grayish tone. Now that the pulp is cleaned and ready, it's time to transform it back into fresh sheets of paper. The first step is dilution. Right now, the pulp is still thick and sludgy, so it's mixed with massive amounts of water until it reaches a thin, soupy consistency. This makes it easier to spread evenly as it moves through the machines. The mixture is then poured onto a massive moving mesh screen where excess water drains away, leaving behind a delicate layer of fibers. These fibers naturally start bonding together, forming the foundation of a new sheet of paper. As the damp sheet moves down the production line, it goes through a series of large pressing rollers that squeeze out even more moisture. The level of pressure applied depends on what type of paper is being made. Fine office paper needs a smoother, even pressing to create a polished texture, while thicker materials like cardboard may go through multiple layers of pressing to add strength. The pressure also helps the fibers bond more tightly, making the paper durable and uniform. Next, the sheet enters the drying phase. This part of the process is like putting the paper through a high-tech clothes dryer, but on a massive industrial scale. The paper is fed through giant heated cylinders that can reach temperatures as high as 130 degrees Celsius. These giant huge metal drums work in a carefully controlled loop, evenly drying the sheet without making it brittle. As it moves through the system, any remaining moisture is evaporated, leaving behind a perfectly dry and structured sheet. Even though it's now dry, the paper still has a rough texture. If it's meant for high quality printing, an extra finishing touch is added. A thin coating of starch or clay is applied to give it a glossy, smooth surface, perfect for magazines, office paper, and premium packaging. On the other hand, if the paper is being made into something sturdier, like cardboard or wrapping materials, a strengthening agent might be added to improve its durability. Once the paper reaches its final form, it's wound into enormous rolls, some weighing up to 30 tons. These massive rolls are then either cut into sheets or sliced into smaller rolls depending on where they're headed next. Some will be transformed into books, notebooks, and office supplies. Others will be used for packaging, newspapers, or wrapping materials. From here, they're packaged and shipped off to manufacturers ready to start their next life cycle. But while paper recycling is an amazing process, it does have its limits. Every time paper is recycled, its fibers get shorter and weaker. After about 5 to 7 cycles, the fibers become too fragile to be turned into strong paper again. That's why some fresh pulp from sustainability harvested trees is often mixed in to maintain the quality of the final product. Even then, when paper reaches the end of its recycling lifespan, it can still be repurposed into egg cartons, insulation, or compost, ensuring that nothing goes to waste. From old newspapers and office memos to brand new books, packaging, and notebooks, the journey of recycled paper is a continuous cycle of renewal. And that's how over 50 million tons of paper get recycled every year, turning old newspapers, magazines, and boxes into something new while helping the planet. What if that soda can that you tossed into the recycling bin this morning could be back on the shelf in just 60 days, looking brand new and ready to go again? And that over 120,000 aluminum cans are recycled every minute around the world, fueling a billion-dollar industry that keeps the planet greener while saving massive amounts of energy. From collecting to melting, this is how 100,000 aluminum cans are recycled each minute in a factory. The journey of recycling aluminum starts the moment you drop an empty can into the recycling bin. From that small action, a massive process begins, spanning cities, industries, and even countries. The first step is collection, and it's a key part of this system. In the United States, consumers can take their used cans to redemption centers, earning small cash rewards while keeping millions of cans out of landfills. Europe runs on deposit refund programs and organized community collection drives. Brazil leads the world with an impressive 98% recycling rate, showing how national systems can make a huge impact. Once the cans are gathered, they're crushed and packed into giant bales. Each bale weighs up to 1,000 kilograms, about the size of a small car, and holds 65,000 flattened cans. Without this compression, loose cans would take up too much space, making transportation inefficient and expensive. But when packed tightly into these compact blocks, they're easy to handle and transport. These bales are shipped to major recycling centers like Novelis in the UK, or large plants in Japan, Germany, and the US. Upon arrival, they're stacked like giant building blocks, waiting to be broken down and recycled into something new. If you're enjoying this video so far, make sure to hit that like button and subscribe to the channel for more content like this. From here, the bales are placed on conveyor belts, heading straight for powerful industrial shredders. These shredders come with 340 horsepower and tear through the bales with ease. Inside, spinning blades rip the aluminum apart, shredding the cans into small, jagged pieces. The sound of metal grinding against metal fills the factory, creating an intense and chaotic atmosphere. But this isn't just about making noise. Shredding reduces the volume of the cans, making them easier to clean and quicker to melt down later. Before they can be melted though, the aluminum needs to be sorted. This step is crucial because aluminum, unlike steel, isn't magnetic, so it can't be separated using simple magnets. Instead, the shredded pieces move down conveyor belts at high speed and pass through an advanced optical sorting system. Infrared sensors scan the flow of metal, identifying and removing anything that isn't aluminum, plastic, glass, or leftover labels. High-powered air jets kick these impurities off the line instantly, ensuring they don't contaminate the clean metal. Even with the optical system doing its job, some steel fragments might still be mixed in. To catch these, the conveyor passes under magnetic separators, which pull out any remaining steel. The process is incredibly fast, but the precision is impressive. What looks like a chaotic blur of flying metal is actually a carefully synchronized system, ensuring that only clean aluminum moves on to the next stage. Now that the aluminum is sorted, it still faces another challenge before it can be melted. The shredded pieces are often coated in materials like protective lacquers on the inside of the cans or colorful paint and labels on the outside. If these coatings are not removed, they can contaminate the melted aluminum and weaken the final product. To solve this, the shredded aluminum passes through high-temperature furnaces built specifically to burn off these residues. Inside the furnaces, the temperature soars past 700 degrees Celsius, hot enough to vaporize the coatings instantly. As the aluminum shreds pass through the fiery environment, you can almost imagine the heat radiating off the walls. The paint and lacquer are reduced to vapor within seconds, leaving clean, bare metal behind. Airflow within the furnace carries away the vapor to ensure it doesn't settle back on the aluminum. This step is critical because even a small amount of leftover residue could cause imperfections in the next stage, smelting. But molten aluminum doesn't cooperate easily. As it melts, it reacts with oxygen in the air, creating a layer of aluminum oxide called dross. This dross floats on the surface, similar to the foam that forms on a cup of hot coffee, but at extreme temperatures. If left unchecked, the dross could mix back into the liquid metal and lower its quality. Skilled operators step in here with long steel paddles, skimming the dross off the surface with precision and care. Skimming dross isn't just about scraping impurities off the surface. It's a combination of science and skilled technique. Modern recycling facilities often rely on flux agents, special chemicals added to the molten aluminum to help impurities stick together and separate more efficiently. Some plants even inject chlorine gas into the furnace. The chlorine reacts with unwanted particles, lifting them to the surface so that they can be easily skimmed away. This combination of manual skimming and chemical refining ensures that the molten aluminum is as pure as possible, ready for casting. Once purified, the glowing liquid metal is poured into molds to cool and harden. One widely used method is direct chill casting, where water sprays directly onto the metal as it leaves the mold, cooling it quickly and preventing cracks or defects from forming. The result? Massive ingots that can weigh up to 27 tons each and measure 10 meters long. It's astonishing to think that each of these giant blocks contains the recycled aluminum from roughly 1.5 million cans. These solidified slabs, or ingots, are the foundation for countless products. New cans, car parts, and even components for airplanes. As they cool, the metal inside becomes dense and strong, creating a perfect base for further refinement. Some facilities take a different approach, using twin roll strip casting to produce thin aluminum sheets directly from the molten metal. But for large-scale operations, casting large ingots remains the preferred method due to their versatility. Once the ingots are fully cooled and hardened, they're ready to be transported to rolling mills for the next stage of their journey. Here, they'll be reheated to around 525 degrees Celsius to relax the metal's internal structure and make it easier to work with. These massive slabs will then pass through powerful rollers that gradually flatten them into thin sheets. It's a bit like rolling out dough, only on an industrial scale. By the time they're done, the aluminum sheets are then as thin as 1/4 millimeter and ready to be shipped off to factories where they'll be transformed into new cans. To put it into perspective, these sheets are thinner than a grain of rice, but strong enough to be rolled into massive reels stretching thousands of meters long. Next, these large reels of aluminum sheets are then sent to can manufacturing plants, where high-speed machines get to work. Cupping presses punch out thousands of shallow cups every minute with remarkable speed and precision. But these cups are just the first step. They're then pushed through a series of forming rings, each one slightly smaller than the last. This gradual squeezing shapes them into the familiar aluminum can, with walls that are thin enough to be lightweight, yet strong enough to hold liquid without bending or breaking. Once the cans are formed, they go through a thorough cleaning and treatment process. Any grease, dust, or leftover particles from manufacturing are washed away, leaving them spotless. But it's not just about cleaning. Each can's interior is treated to prevent any reaction with the beverages it will contain later, ensuring the drink stays fresh and uncontaminated. Meanwhile, the can lids are made separately. Sheets of aluminum are cut into discs and pressed into perfectly formed lids. A rubber sealant is applied around the edges to create an airtight fit, guaranteeing that once the cans are filled and sealed, they stay that way. The pull tabs are molded and attached using precision machines, completing the lid's design. Interestingly, the technology behind this process is closely related to aerospace engineering. The aluminum alloys used to make beverage cans are very similar to those found in rockets, so the can holding your soda is more advanced than you might think. Economically, aluminum recycling is a giant. The industry creates over 100,000 jobs in the US and generates billions of dollars in revenue each year. By keeping materials in use and reducing the need for raw resource extraction, it plays a vital role in promoting a circular economy. This system ensures that products are continuously reused instead of being discarded, reducing waste and environmental harm while boosting long-term economic growth. Finally, after the cans are formed, cleaned, and sealed with their lids, they're ready for their final journey. They are then filled with soda, beer, or other beverages and shipped to stores around the world. The cycle doesn't stop there. In just 60 days, the can you're holding today could be collected, melted down, and reborn as a brand new can, clean, shiny, and ready to start its journey all over again. That's the beauty of aluminum. Endless recycling, endless possibilities. And that's how over 100,000 aluminum cans are recycled every minute, giving them endless new lives while saving energy and protecting the planet. Did you know that recycling just 6 steel cans saves enough energy to power a 60-watt light bulb for 26 hours? That means that the steel frame of a skyscraper could have once been a rusted-out car. The beams holding up bridges, they might have started as an old refrigerator. But how does scrap metal get transformed into high-quality steel used in construction, transportation, and manufacturing? From shredding to smelting, this is how factories recycle 1,000 tons of steel every minute, without ever running out of raw material. Steel recycling doesn't start in some high-tech factory. It begins in the real world, where mountains of old metal are waiting for a second chance. Scrapyards, demolition sites, abandoned industrial plants, you name it. If there's steel, it can be reborn. Unlike plastic or paper, steel never wears out. It can be melted down and reshaped forever, making it one of the most valuable materials on the planet. Every minute, truckloads of scrap steel roll into recycling plants. Some carry crushed cars, others haul chunks of torn down bridges, rusted out shipping containers, or leftovers from construction sites. Even the old washing machine that rattled like a jet engine before it finally broke down, it all ends up here, ready for transformation. Steel doesn't just show up in a factory, ready to melt. It's usually a mess. It's covered in plastic, tangled with rubber, and sometimes even coated in toxic chemicals. Before it can be recycled, all of that junk has to go. Luckily, the heavy lifting is done by machines. At massive processing plants, powerful magnets yank out anything iron-based, while high-tech scanners quickly sort out aluminum, copper, and other metals that don't belong. But not everything can be separated by machines. Some pieces still have plastic or wiring attached, so workers step in to strip it away by hand. In some places, oversized chunks of scrap get squeezed into massive cubes to make them easier to haul. But it can't go into the furnace in big, bulky pieces. It has to be broken down first. That's where the cutting, crushing, and shredding happens, turning huge chunks of metal into smaller, manageable pieces. First, hydraulic presses flatten oversized steel with massive force, crushing everything from car frames to steel beams. The noise is intense, metal crunching, machines humming, and sparks flying. Next, industrial shredders take over. Their spinning steel blades tear through old appliances, car parts, and sheet metal in seconds. But some steel is too thick for shredders, so industrial shears slice right through it like giant scissors. For the toughest materials, workers use oxy-fuel and plasma torches. These generate extreme heat, melting solid steel in seconds. By the end of this stage, the steel is reduced to smaller pieces, about 20 to 50 centimeters long. Then it's loaded onto conveyor belts and dropped into massive steel baskets, each holding up to 110 tons. From here, it's ready for the furnace. This is where steel goes through its biggest transformation. Giant steel baskets, packed with shredded metal, are lifted high and tipped into electric arc furnaces, some of the hottest places on Earth. Unlike traditional blast furnaces, which burn iron ore and coal, electric arc furnaces run on electricity. This makes them far more energy efficient and environmentally friendly. Inside, carbon electrodes generate powerful electric arcs, heating the furnace to over 3,500 degrees Celsius, aka 6,332 degrees Fahrenheit, which is hotter than the surface of the sun. Within minutes, solid steel melts into a glowing white hot liquid, swirling like lava. As the steel melts, unwanted materials like dirt, plastic, and paint burn off or separate, forming a foamy layer of slag that floats to the surface. But even this isn't wasted. It's collected, cooled, and crushed for use in cement and road construction. Even though electric arc furnaces are a cleaner way to recycle steel, the industry is always looking for ways to improve. Some factories are now replacing coal-based fuel with shredded plastic and rubber, reducing waste while keeping the process just as effective. The steel is melted, but it's not ready yet. Before it can be shaped, it needs to be refined to make sure it's strong, durable, and safe for use in buildings, cars, and machines. One problem is trapped gases. During melting, nitrogen, hydrogen, and oxygen mix into the steel. If they stay, they create weak spots that make the metal brittle. To fix this, factories inject argon gas, which pushes these gases to the surface so that they can be removed. Next comes alloying, where elements are added to improve the steel. Manganese makes it stronger, nickel helps prevent rust, chromium adds durability, and molybdenum increases heat resistance. Even small changes in these elements decide how the steel will be used. Once refining is done, the molten steel is finally ready to be shaped. With its composition perfected, the molten steel moves to casting, where it is poured into molds and solidified into usable shapes. This stage is important, as the way steel cools and solidifies determines its final structure, strength, and durability. Most factories today use continuous casting because it's faster, more efficient, and reduces waste. Instead of pouring molten steel into large molds, letting it cool, reheating it, and then shaping it, like the old ingot method, continuous casting keeps the steel moving, saving energy and preventing defects. Molten steel flows through water-cooled copper molds, which help it solidify quickly. As it cools, it slowly transforms into long rectangular billets, thick slabs, or cylindrical blooms, depending on what it will be used for. The glowing hot steel bars come out in a semi-solid state, firm enough to hold their shape, but still soft enough to be molded. Next comes secondary cooling. The newly cast steel moves along a controlled path, where it is sprayed with water or air to fully harden. The cooling process has to be just right. Too fast and the steel can crack, too slow and it won't be as strong. Once the steel has partially hardened, it is guided through massive rollers that help us shape it further. These rollers are hydraulically controlled, applying enormous pressure to maintain uniform thickness and eliminate inconsistencies in the metal's structure. Unlike older ingot casting, which required steel to be cut, reheated, and reshaped multiple times, continuous casting allows factories to skip several time-consuming steps while producing steel with fewer defects. This innovation has made steel production faster, more cost-effective, and more environmentally friendly. After passing through the rollers and fully cooling, the steel is ready for hot rolling, one of the final transformative processes in its journey. Now, the steel enters the hot rolling mills where it takes its final shape. But before it can be molded, it has to be reheated to an incredible 1,270 degrees Celsius, aka 2,318 degrees Fahrenheit. Hot enough to make it flexible without breaking. Once it's glowing red hot, the steel moves through a series of powerful rollers. These rollers press and stretch the metal, shaping it into precise dimensions. The intense pressure forces the steel into its final form, ensuring it meets exact industrial requirements. The rolling process depends on what the steel will be used for. Structural steel, like H-beams and I-beams, is made strong enough to hold up skyscrapers, bridges, and heavy machinery. Reinforcing bars are shaped for concrete reinforcement, adding strength to buildings and roads. Thin steel sheets, on the other hand, become car frames, home appliances, and industrial equipment. But hot rolling isn't just about shaping, it also strengthens the steel. The extreme pressure refines its internal structure, making it more durable and resistant to wear. However, this process leaves behind a rough, oxidized layer called scale. To remove it, factories use high-pressure water jets that blast away the surface impurities, leaving behind clean, polished steel, ready for the next stage. For steel that needs to be even stronger and more precise, the next step is cold rolling. Unlike hot rolling, this process happens at room temperature, where the steel is pressed even tighter to make it harder and smoother. This makes it perfect for products that need extreme accuracy, but there's a catch. Cold rolling makes steel more brittle. To fix this, some batches go through annealing, a heat treatment process that softens the steel just enough to keep it strong but flexible. At this point, the steel might need further shaping. Depending on its final use, it could be cut, bent, stamped, or welded. Advanced machines, like laser cutters and industrial presses, make sure every piece is the exact size and shape needed. Once all of this is done, the steel moves on to the final steps: coating, finishing, and shipping, getting it ready for use in industries around the world. Now that the steel has taken its final shape, it's time for precision cutting. Giant industrial saws, high-powered plasma cutters, and automated shearing machines slice right through beams, sheets, and rods, ensuring each piece is the exact size required. Even the smallest miscalculation can lead to wasted material, so accuracy is everything. But steel isn't just about shape, it needs protection. Without proper coating, it can rust, corrode, or weaken over time. That's where different finishing processes come in. For outdoor structures like bridges and skyscrapers, steel is galvanized. This means it's coated in a protective layer of zinc to prevent rust and corrosion, allowing it to withstand extreme weather conditions. Meanwhile, steel used in food packaging and household appliances go through tin plating. A thin layer of tin prevents oxidation, making it safe for canned goods, beverage containers, and kitchenware. Some steel is painted or powder-coated to improve durability, resist wear and tear, or enhance its appearance. Other coatings are designed for specialized uses. Some improve electrical conductivity, while others provide heat resistance for extreme conditions. Before the steel leaves the factory, it goes through strict quality control. High-tech scanners, ultrasonic tests, and X-ray inspections check for invisible flaws. Strength tests measure how much force the steel can handle, while hardness tests ensure it meets industry standards. Only after passing these tests is the steel bundled, labeled, and shipped. It's loaded onto trucks, trains, and cargo ships, heading to factories, construction sites, and industries around the world. Soon, this steel will become part of cars, airplanes, buildings, machines, and even spacecraft. And the best part? When its job is done, it can be melted down and recycled all over again, keeping the cycle going. What was once a pile of scrap is now ready to help build the future. And that's how 1,000 tons of steel is recycled every single minute, turning scrap into high-strength metal while keeping waste out of landfills. Which part of the process surprised you the most? Let us know in the comments below. Don't forget to like, subscribe, and stay tuned for more behind-the-scenes factory processes.